Hi everyone. It's a pleasure to be here with you to present the Progressive Insular Cooperative GP that I will call simply by PIC GP during the presentation. This is a multi-class classification algorithm, and its first motivation was to develop an efficient multi-class classification GP algorithm. The choosing strategy was to work with one versus all classes comparison. And it means that we have one specialized solution to be responsible for classifying each target class. It tends to be more efficient because then the specialist solutions will have to capture only the information of its own class, what do not happen if we have a single solution in charge of modeling the whole complexity of the system. However, this strategy creates a requirement of an extra step to decide which class will be the final prediction in the case of more than one specialist giving a positive result for its own class. There are some approaches in the literature, and we choose to use the logistic output of the specialist individuals as inputs of the softmax function. This upper level structure is a tree with the softmax at the root node, and it's called Ting. In PIC GP, the teams evolve at the same time with the specialist individuals. Thus, PIC GP permits the evolution of highly specialized individuals, but also the evolution of the teams themselves, since not always highly specialized individuals will necessarily work better than when they work together. The second motivation was to have a team-based GP in which the balance between competition and cooperation amongst the specialists can be controlled. And why this is important? Because the competition between solutions will favor the search space exploitation, while the cooperation among different specialists will favor the search space exploration. In a traditional GP, this balance is driven by the selection method as well the crossover and mutation rates. But in a cooperative GP, in addition, the intensity of cooperation amongst the specialists will also help to tune this balance. And it's not clear in the available literature on how to benefit from the balance between cooperation and the evolution of highly specialized individuals to properly explore and exploit the search space. Lucas Spector, 1996, found that restricting the interaction between the individuals of the same specialization improved the algorithm performance. In another study, Solik from 2000, concluded that heterogeneity among teams is necessary, but not enough, while individuals' highly specialization that is related with heterogeneity is a key factor for improving the algorithm performance. And we also were motivated by helping to clarify this question. So how PIC GP works? As said before, it works in two levels, one for the specialist evolution and another for the team's evolution. The specialist populations is initialized with the humped half and half method, and the trees are then assigned to the class to which they perform better. But in order to have subpopulations all with the same number of individuals, the worst individuals of the subpopulations with more specialists are randomly assigned to other subpopulations. And here we have the subpopulation working as teams that are subpopulations that can interact. The selection method in PIC GP is modified to work with two individuals at a time. The first parent, the selection of the first parent helps to control the balance on the number of individuals specialized in each target class. The first parent is selected from a specific subpopulation, choosing deterministically by the algorithm to guarantee this balance. The second step of PIC GP selection will control the intensity of cooperation among the specialists. To do that, the fitness of the individuals, the specialist individuals of different classes from the first parent is weighted by the cooperation intensity rate parameter. It receives values from 0 to 1 and weights down the solution's fitnesses in such a way that if it's 1, the second parent will be chosen as if the individuals were all in the same population, allowing the maximum of cooperation among specialists. On the other hand, if it's 0, it will reduce to the maximum the selection of individuals with different specializations, which means that it will decrease to the maximum the cooperation between specialists. After the crossover and mutation, the individuals are assigned to the class, so to control the specialist cooperation over the entire algorithm evolution, the cooperation intensity rate can be decreased over the generations. Its decrease is set by another parameter that is the cooperation intensity rate decrease rate. However, when using the tournament selection for the second parent, a 0 fitness individual can be chosen. And so, in addition to these 2 parameters, a third one is needed. That's the phase change, the generation in which the individuals are not allowed to cooperate anymore. And so the DIMs become islands that are subpopulations that do not interact anymore. The teams population is initialized with teams formed by specialists selected with roulette wheel selection from specialist subpopulations. The team crossover exchange between teams entire specialist individuals from the same class, and the team mutation exchanges a specialist by a new one taken from the specialist population. And importantly, from the second generation and on, the team's population is replaced half by its offspring and half by new teams formed by individuals from the evolved specialist population. So in the first experiments, we'd like to study the behavior, not only the performance of the algorithm. To do that, we used the iris data set. It has only 3 classes, and it's interesting because the setosa class is linearly separable, so it's quite easy to classify. And the versicolor class is the one with the feature values mixed in between the other 2 classes. So it's the hardest one to classify. All experiments were run 30 times, with each one with a different data partition. The training set had 80% of the observations, and the test and validation sets had each 10% of the observations. And here we will present the main results of these experiments. First, the specialist selection method experiments. In this set of experiments, we are interested in studying the effect of the selection method in the cooperation between different specialists. The selection method for the first parent controls the selection pressure, as in a traditional GP, but inside the specific subpopulation. On the other hand, the selection of the second parent also controls the amount of cooperation between the specialists. The tested selection methods were these combinations of the roulette wheel and tournament with size 3 and 5. This figure shows the mean and one standard deviation of the number of interactions between 2 specialists of different classes over the algorithm evolution using these selected methods. Notice that the bigger the tournament for the second parent, the more cooperation among different specialists happen in each generation. This happens because the first step of the tournament selection is random. More specifically, it's not related to the fitness of the individuals, but it's affected by the number of specialists in each subpopulation. And since the setosa class is the easiest to distinguish, its subpopulation tend to have more individuals. What can be seen in these plots that show the number of individuals in each subpopulation through the algorithm evolution for the experiments using tournament selection with sizes 3 and 5. This added to the fact that the class of the first parent is defined deterministically by the algorithm to balance the size of the subpopulations, produced the pattern that we can see. The cetose specialists were favored in the second parent selection, and it increased the rate of cooperation, since approximately 2/3 of the first parents weren't from this class. Now, let's see the cooperation intensity rate, or CIR, experiments results. In this set of experiments, we were interested in studying the influence of the cooperation intensity rate on the algorithm dynamics. These were the tested CIR values, and it was always kept constant over the algorithm evolution. Again, this plot shows the mean and one standard deviation of the number of interactions between individuals of different specialization classes. The specialist cooperation decreased slightly along the evolution with experiments with CIR from 0 to 0.4. For CIR equals to 0.6 and 0.8, it reached a maximum in the early generations and decreased afterwards. And for CIR equals to 1, in contrast, they steadily increased along the evolution of the algorithm. In general, the specialist cooperation increased with the increase of CIR as expected. However, this correlation was not linear because it also depends on the number of individuals in each class specialization, since the tournament was used as selection method. For CIR values from 0 to 0.4, the interactions among specialists were stable because the number of individuals in each specialization subpopulation was stable and balanced. For CIR equals to 0.6 and 0.8, the cetose specialists started to prevail at the expense of the versicolor and virginica specialists, but this pattern tended to smooth with the algorithm evolution more intensely for CIR equals to 0.6 and less for CIR equals to 0.8. And this reflected the amount of cooperation among specialists. For CIR equal to 1, the prevalence of cetose individuals lasted for the entire Tim's phase, and this produced the pattern that of the specialist interactions over the algorithm evolution. The CIR value was also important for the mean fitness of the class subpopulations during the evolution, as it can be seen in these plots that show the mean fitness for each class through the algorithm evolution for each CIR value experiment. With higher CIR values, that is, with more cooperation between specialists of different classes, the mean fitness of the class subpopulations increased early for all classes. And interestingly, the mean fitness of specialized subpopulations increased more with the phase change for smaller values of CIR. What also can be seen in these plots on the difference between the mean fitness of the subpopulations 50 generations before and 50 generations after the phase change that converted the subpopulations from DIMs to completely isolated islands. To highlight this point, this table shows this result in numbers. Here we have the mean fitness of specialist subpopulations 50 generations before and 50 generations after the phase change for each CIR value experiment. The both values are the higher values for each class before and after the phase change. As a tendency, the bigger the CIR, the smaller the CIR increase with the phase change for all subpopulations. For the weakest classifiers, those responsible for classifying the versicolor, that is the hardest class to discriminate, the higher value of the population mean fitness was achieved with CIR equals to 1. And on the other hand, for the strongest classifiers, those responsible for classifying the easiest class, cetosa, it was achieved with the CIR equals to 0. This indicated that a higher CIR value favored the improvement of the subpopulation of weaker classifiers. And two interesting conclusions can be drawn from these experiments. First, the DIMS phase, when there is cooperation among specialists, helped especially the weaker classifiers. Second, the island phase, when there is no cooperation at all, is also important for all subpopulations to evolve. And so both DIMs and islands seem to be important for achieving the best algorithmic performance. And in order to assess the competitiveness of PIC GP, we compared its performance with the performance of other algorithms using the thyroid and the yeast dataset from the UCI machine learning repository. The main results are shown in these tables. The left one is for the thyroid dataset, and the right one is for the yeast dataset experiments. The other algorithm results were reported in this reference, Zhang et al. From 2017, and it was considered comparable because we have used exactly the same data partition as them. For the thyroid dataset, the PIC GP outperformed 9 of the 11 tested algorithms, and it was slightly outperformed only by stochastic gradient boosting decision trees and random forests. For the yeast dataset, the PIC GP outperformed 10 of the 11 algorithms. So the experiments with IRIS dataset indicated that the cooperation among specialists can be helpful, especially for the weaker classifiers, and that the island phase, that is, the absence of cooperation, is important for all subpopulations, which means that both DIMs and island phases are important, and the proper combination of them will depend on the problem. This elucidated a major question that had no clear in the available literature, that the Ting GP can benefit both from the cooperation among specialists of different classes and from a more restricted process where only the interaction among individuals specialized in the same class is allowed. And combining the individuals and the team evolutions and using just 3 simple parameters, the PIC GP achieved a very good performance in the preliminary studies. Thank you all. That's it. If you have any question.
Thank you very much. I currently do not see any question in the chat, so I ask the attendees to formulate question if they have one. I have one actually. Broadly speaking, your method is about let's say concurrent evolution of partial solution to, let's say, sub problems of the main problem. Do you think that something that you found in this study is applicable also to other cases in which you evolve at the same time a sort of ensemble for, let's say, broadly speaking, complex problem?
Yes, I think so. Even we can think on a version of this cooperative in a regression problem, for example, in which the solutions are specialized in some part of data and they can cooperate during the evolution. If you can have solutions that can cooperate, that can interact during the evolution, yes, I believe it.
Okay, thank you. I found particularly interesting the fact that you have a second population that is especially devoted to find a way to combine the other individuals. That would be interesting also in other applications. Okay, so we are comfortably on time because the next speaker is scheduled in more or less 4 minutes, right? Ting? So we can, if there are other questions, I strongly suggest you to do them now so that we have plenty of time for discussing the answers.
Could I ask a question?
Yes, please go, Bill.
So I'm sorry if I didn't get this, but at various points on your graphs you were talking of a phase transition. Can you give probably you explained this and I missed it. Perhaps you could go over that again?
Okay, the phase change is when the superpopulations are not allowed to work together to cooperate anymore. So we start the algorithm with themes and the superpopulations that can interact, and it's a parameter of the algorithm. So you decide in which generation it will happen, that these superpopulations will not be allowed to cooperate anymore. We have the decreasing of the cooperation intensity rate parameter. But as I said, if you are using the tournament selection for the second parent, a zero fitness individual can be selected. So in order to do not allow the cooperation among individuals of different specializations anymore, we have this extra parameter. That's the phase change when we totally convert the deans into islands.
And this is externally imposed. This is something that you decide and you enforce it on the population.
Yes, it's a parameter of the algorithm. So if you don't want to have this imposition on your evolution, you can not have these parameters set. You can work with themes for the entire evolution.
Oh, nice. Okay. Okay. And several of your graphs seem to, well, there were two things that happened. One was it didn't appear to make any difference, and the trace continued more or less as was. And in the other cases, you have a very different population afterwards. There was a very abrupt change. And I wondered if you could explain why one was continuous and why the other was discontinuous.
Why? Let me see if I got to your question properly. But the experiments showed that the DEEMS phase helped the weaker classifiers, right? So it will, if we will have a more longer continuous phase, the DEEMS, or if you have a more longer island phase, will depend on the problem.
Okay, so where we were seeing different behavior, that's because we were looking at different problems.
Yes.
Okay, sorry, I missed that. Okay, thank you.
Thank you too.
Okay, thank you, Bill. Thank you, Karina, again for your nice talk and for the answers to the questions.